Welcome back to Lucky Naresh Physics channel. Students, in this session I am going to discuss about introduction, inconsistency of Ampere's circuital law, displacement current, consistency of modification of Ampere's circuital law. Introduction. Students, you know that when charge in motion it produces magnetic field. In the same way, the change in magnetic flux produces electric current. So, Maxwell predicted that energy will travel in the form of electromagnetic waves and whose speed is equal to the speed of light. So, he concluded that light is an electromagnetic wave. Later, he found that there is an inconsistency in Ampere's circuital law. How he found that? Look at here. Ampere's circuital law. You know that the line integral of magnetic field around a closed loop is equal to the mu naught times of current flowing through that loop. Here, Maxwell found that there is an inconsistency in Ampere's circuital law. How he found? For that, he took one circuit here. In that circuit, he connected capacitor with cell. When switch is on, current will flow. When charge on capacitor increases, current in the circuit decreases. When capacitor is completely charged, then there is no current in the circuit. While charging capacitor, there is no flow of current between the plates of the capacitor. Here, he considered two loops. One loop is outside the capacitor, that is C1, and the another loop is in between the capacitor, that is C2. For loop C1, he applied Ampere's circuital law. Look at here. For loop C1, line integral of magnetic field around a closed loop C1 is equal to mu naught times of current flowing through that loop. This is equation 1. Now he applied Ampere's circuital law for loop C2. For loop C2, line integral of magnetic field over a closed loop C2 is equal to 0. Here why we got 0? Because while charging capacitor, there is no flow of current between the plates of the capacitor. So through loop C2, there is no current is flowing here. Okay. So through loop C2, there is no current here. So we got line integral of magnetic field around a closed loop C2 0. This is equation 2. See, in second circuit, if you look at here, in second circuit, Maxwell considered that if these two loops are very close, then their magnetic field must be equal. Look at here. If these loops are very close, then magnetic field produced by loop C1 will be equal to magnetic field produced by C2. Look at here. Then line integral of C1 VDL is equal to line integral of C2 VDL. So this is equation 3. Here, this equation 3 contradicts equation 1 and 2. So, Maxwell found there is an inconsistency in Ampere's circuital law. Why that inconsistency happens here? There is something missing. That something he found the change in electric field through the loop C2 between the plates of the capacitor. The change in electric field with time through loop C2 later he named as displacement current. Now we will discuss about displacement current. Now displacement current. The current which comes into play along with conduction current when there is a change in electric flux with time is called displacement current. Look at here. Displacement current ID equal to I suffix D, that means displacement current. ID equal to epsilon naught d phi E by dt, that means change in electric flux with time. Okay. Now total current. I equal to conduction current plus displacement current. Now Maxwell modified Ampere's circuital law. In the place of total current, he took conduction current and displacement current. Look at here. Maxwell modifies Ampere's circuital law, ACL. ACL means Ampere's circuital law. That is line integral of magnetic field around a closed loop, mu naught times of current. Instead of total current, he took conduction current and displacement current. IC plus ID, that is equal to mu naught IC plus, instead of ID I can write this equation, that is epsilon naught d phi E by dt. Epsilon naught d phi E by dt. So here Maxwell modified Ampere's circuital law with displacement current. So we got the equation here. So that's about modification of Ampere's circuital law. Now we will check the consistency of modification of Ampere's circuital law. Now consistency of modification of Ampere's circuital law. Look at here. See, from the circuit diagram, from loop C1, for loop C1, if you apply Ampere's circuital law, line integral of magnetic field around a closed loop C1 is equal to mu naught times of I. For loop C2, line integral of magnetic field over around a closed loop C2 is equal to mu naught times of displacement current. See, already we discussed now. Here displacement current comes into play between the plates of the capacitor in the loop C2 when there is a change in electric flux with time. So I replaced displacement current here, that equal to mu naught. Displacement current means we can write epsilon naught d phi E by dt. Epsilon naught means permittivity of free space. D phi E by dt means change in electric flux with time. This is equation 2. First one I will consider as equation 1. Okay. Now if Q is the charge on the plates of the capacitor, then the electric field between the plates of the capacitor is, look at here, if Q is the charge on the plates of the capacitor, then electric field E equal to Q by epsilon naught A. From that I will write E into A equal to Q by epsilon naught. E into A means, that is electric flux. Phi suffix E is equal to Q by epsilon naught. So this is equation 3. Now I will substitute this equation 3 in equation 2. Look at here. Now substitute equation 3 in equation 2. Then equation 2 implies line integral of magnetic field around a closed loop C2 is equal to mu naught epsilon naught d by dt. Instead of phi E, I will substitute this equation 3, that is Q by epsilon naught. Here this numerator epsilon naught, denominator epsilon naught will be cancelled, so we will get mu naught into dq by dt. dq by dt means, that is rate of flow of charge. Rate of flow of charge means current. So I can substitute here mu naught in the place of dq by dt. I will substitute I, that is current. So finally I got equation 4, that is line integral of BDL around a closed loop C2. Line integral of magnetic field around a closed loop C2 is equal to mu naught times of I. So from equation 4 you can say that, which gives the consistency relation with equation 1. This consistency happens due to displacement current. So that's about consistency of Ampere's circuital law. So here displacement current gives the consistency for Ampere's circuital law. Students, thanks for watching my video. In next session, I will discuss about Maxwell equations. Thanks for supporting me. Please subscribe and click the bell icon for all notifications. Thank you.